Hello, everybody. Come on in. How's it going, Sam? How you doing, Tony? Randall? Kevin? Your towels here. Got about 2 minutes for class start. Feel free to ask me any questions if you have any. Looks like everybody's good to go then. I'm going to start class tonight with just mentioning a couple things. I got one problem I wanted to do. I didn't get enough time to do it last time, so I'm going to do that from chapter 18. And then I'm going to refresh your memory, which I did at the end of the last time's video, so you can look on there as well. But at the very end, I told you what's relevant when it's already recorded. But the main thing is I want to talk to you about how you're going to see them in the homeworks to some extent, and you might accidentally see some of the topics that I will not be putting on the test. Some of those might show up on the practice test. Ignore them when they happen, but the main thing is I'm only testing you on the stuff that I'm going to tell you about today. So we've got about a minute left. Still no questions? I have to bite the bullet in a second and crush this mint so I won't have it in my mouth flipping all around waiting to choke me to death. All right, well, it's 5:20. I guess I'll go ahead and get started then. All right, let me first go ahead and share my screen. I want to show you basically the table of contents for chapter 18. So here's chapter 18. What I did do is I used the kinetic theory to basically derive sort of the average kinetic energy per molecule, the average kinetic energy per molecule in an ideal gas. And from that, we were able to figure out what the root mean square velocity is of a molecule for a given temperature, that sort of stuff. That's something you should be able to do. You should be able to calculate the kinetic energy of an individual atom or molecule. You should be able to give me the root mean square of the individual atom or molecule. You should be able to tell me what the total kinetic energy of all the atoms and molecules, for instance, are in a particular sample of gas. This is sort of that stuff that we saw in section 18.1. Then you should be able to use this. So this is the Maxwell-Boltzmann distribution that we talked about. And specifically what I mean is you should be able to use that to do an integral to calculate the average velocity v bar, which is literally you take this function right here, and notice it's already got a v in there. There's a v squared there and a v squared there. You're going to multiply this by v because this is more or less, when you multiply it by dv, it's a probability density. So if you multiply it by v, then you're calculating the average velocity. If you multiply it by v squared, then you're calculating the average square of the velocity. If you calculate it by v times v cubed, it'd be the average cube of the velocity. I expect you to be able to do at least the average velocity, which is multiplying it by v, and then integrating it. The example below does it, and in fact, I suggested that was an extra credit problem you guys can do, even though the whole solution is right here in this example. It's actually on the next page. So anyways, that's one of the things you should be able to do. You could also be asked to verify that that's n. In other words, if you take the integral from 0 to infinity of f of v dv, that should give you n, the total number of particles that was assumed when Maxwell derived this. So that's the things you got to be able to do from this section 18.1 and 18.2. The rest of the stuff, if you look in this table of contents that says kinetic energy near absolute zero, that's a concept that I discussed with you. So with regards to the bad guy, for instance, in The Incredibles, distribution of molecular speeds, that's that function I just told you, or that's the idea of a function existing. And then Maxwell distribution is the actual result, as James Clerk Maxwell did. Calculations using the Maxwell distribution. Again, that's the integral and the derivative that you should be able to do. I'm getting ready to work the derivative for you. Real gases and change of phase. That is, again, more concept stuff you should know, but you get it from your reading. Evaporation, vapor pressure, and boiling. Again, more stuff like the real gases. Vapor pressure and humidity. Yeah, that's an important topic again, but this is more conceptual stuff, not stuff that you actually have to work out. Once you get down to section 18.5 or 18.5, no, 18.4.4, this one, partial pressure and humidity. That is one of the few problems I expect you to be able to do that I haven't shown you an example of, but the book does, and it's really simple. Basically, there's a table. You do it. I'll go over that in a second. Temperature decrease of boiling water with altitude. That again is a big concept, something you should understand, and something you hopefully already got from a course in chemistry if you've had one. But van der Waals equation of state, that's actually van der Waals, and there's Clausius as well in there. I think those, as well as all these other questions I'm talking about, are fair for homework, and they'll be on the homework. And I tried to cut them out mostly out of the practice test, but there might still be a few in the practice test. But the important thing is to know that all these things that I'm talking about should not be on the test unless I explicitly tell you. So far, all I've told you that it should explicitly be something you know for the test is using the Maxwell distribution specifically, and by taking an integral so that you can calculate V bar, taking an integral so that you can see just the integral of f of v dv is in fact n, and taking the derivative of f of v so that you can find, for instance, the most probable speed, which is what I'm getting ready to show you. You also need to, of course, be able to use that kinetic energy that we derived. K average is equal to 3/2 K sub B times T. That's the Boltzmann constant times T. And then use that to realize that the average kinetic energy is listed as 1/2 times the mass of the molecule times V bar squared. Okay, that's the root mean square velocity when you do, or V squared bar, I should say. That's the root mean square velocity. So those things all in this section right here, 18.1, is completely fair. The molecular speed, specifically those three things I talked about, the distribution of speeds and the Maxwell distribution, that's the main things you got to know from that. This other stuff, the van der Waals equation, mean free path, and diffusion, perfectly fair for me to want you to do it on the homework. Not supposed to be in the practice test, but it might pop up there by accident. Just know it's not going to be on the test. So really all that's on the test is calculation of partial pressure and humidity and Maxwell distribution, those three ways I told you, and then using K bar equals 1/2 M V bar square, or excuse me, V squared bar, which is VRMS squared. Okay, any questions on that? All right, so let me show you that partial pressure and humidity situation. So what we're talking about specifically is this formula right here, relative humidity. Relative humidity is the partial pressure of H2O divided by the saturated vapor pressure of H2O times 100%. In order to do this, you need this table right here. So obviously, if I give you a problem on that in your homework, it's not that table, it's not that place. If I give you this problem on a test or on the homework, you're expected to actually use this. So, man, if I can find it. Maybe it was 2 sections ago. Must have been what it was. So relative humidity is not there. Here you go. I'll just click on the link to it. So it says the relative humidity is the partial pressure of water. Remember from Dalton's law of partial pressures, divided by the saturated vapor pressure of water. And then basically you just move the decimal 2 places to the right and stick in a percent symbol on the end. So right here it says on a particular hot day, the temperature is 30 degrees Celsius. and the partial pressure of water vapor is 0.030 atmospheres. What is the relative humidity? So you see they've given you the partial pressure of water vapor and they've given it to you in atmospheres. That's what you've got to know going into the problem, because now you've got to look up the saturated vapor pressure in atmospheres. That's specifically why I said that's the part you had to know. So I click on table 18.2 and we said, actually, did I say it was 30 degrees Celsius? Yeah, it's 30 degrees Celsius. So you see at 30 degrees Celsius, you have the saturation vapor pressure could be 0.042 atmospheres, or it'd be 4.24 times 10 to the third pascals. The main thing is that one they gave us was an atmosphere, so you want to use that. So now that we have that, we're going to take 0.03 and divide it into 0.042. So 0.03 divided by 0.042 gives us the answer, as they did here, 0.03 divided by 0.042, and then move the decimal 2 places to the right, stick a percent symbol on it. So that's it. That's the crux of that calculation. So I do not mind that one appearing on a test, obviously. Okay. It can appear in homework, it can appear in a practice test, and it can appear in the test. So far we've got those kinetic energy per molecule, total kinetic energy of n molecules, for instance, and root mean square velocities for a molecule, all that stuff that comes from the kinetic theory and kinetic energy equations. Then we've got those three versions of Maxwell-Boltzmann, the Maxwell distribution. The three ways we could use it, which I said was integrating to find the average velocity, integrating v times f of v dv, or actually technically your book's using a nu, the Greek letter nu, which looks sort of like a v, but anyways, it's the integral of nu times f of nu d nu, and you're going to integrate that to get the average velocity. You also should be able to integrate 0 to infinity of just plain f of nu dv nu, and that should give you n, the total number of atoms that were hypothesized, or molecules. And then finally, the last part is you should be able to take the derivative of that f of nu to find the most probable value, because one of the fundamental things we learned with calculus is calculus allows us a method to find extrema, which could mean maxima, minima, or points of inflection. So it really helps to know not only how to calculate an extrema, but to tell exactly which extrema it is. So there's a test. You should know that by now. Hopefully you knew it from the first semester. Hopefully you knew it from the first semester of calculus. But I will just remind you that you take the derivative set of equal to 0. That is the test for an extrema. What ends up happening there is you either get a maxima or a minima, or you get a point of inflection. And the way you test whether it's a point of inflection, maxima, or minima is you take a second derivative using the result you've had by setting the first derivative equal to 0. You then plug that result into the second derivative, and if it comes out to be, for instance, negative, then it's a maxima. If it comes out to be positive, then it's a minima. And if it comes out to be 0, it's a point of inflection. Okay, so let's turn back to now the Maxwell distribution, and I'm going to show you how to calculate the most probable value. So let me kill this. I'm going to stop sharing my screen there. And I'm going to start sharing my screen here using my iPad. It should come up pretty soon now. Maybe. By the way, I'm writing the Maxwell-Boltzmann distribution as if it's f of v, just because v is a little easier to write than nu, but your book definitely has nu instead of v. So the expression is 4 pi n times parentheses m over 2 pi kt. That's all to the 3/2 power. And then you have a v squared times e to the negative mv squared over 2 kt. Okay, so you see that the numerator of that exponent is really 1/2 mv squared. The denominator is just kt, but that's the key point. What I want to take is I want to take df over dv there I go, writing the nu this time instead of the v. Of course, it's going to happen as soon as I tell you I'm not going to do it. All right. So now that I have that, I'm going to take the derivative and set it equal to 0. If you'll notice, really what we're looking for is things that can make the actual derivative equal to 0. So a common factor out in front isn't part of that. So I'm just going to pull all that out to the side. 4 pi n m over 2 pi kt to the 3/2 power. Then I'm going to say d by dv of v squared e to the negative mv squared over 2kt. And then all that will be set equal to 0. Obviously, you can divide through by this part, and you'll just have the derivative of that equal to 0. Now, that's a product, so that's pretty straightforward. From that, the product is, or the derivative of the product is, I'm going to take the derivative of the first one, the first factor, which is v squared. The derivative of that is 2v. And now I'm just going to write the second factor, which is e to the negative blah, blah, blah. I don't have to write that every time. I'll just leave it like that. That's fine. Now I'm going to add to it the next process where I'm going to multiply the first factor times the derivative of the second. So in this case, I'm going to get v squared. And now I got to take the derivative of e to the negative mv squared 2kt. Well, the derivative of e to the anything is e to that same thing, and then the derivative of that thing that it was raised to. So I'm going to go ahead and take the derivative of the exponent. The derivative of the exponent is 2mv over 2kt. So that's just mv over kt like this. And there should be a minus there. So I'll put a minus in there barely. Sorry about that. Actually, let me go ahead and make it a little more obvious that I put a negative in there so it don't look so bad. So it's negative mv over kt. And now it's also multiplied by e to the dot, dot, dot again. That's all equal to 0. The main thing is I didn't need to do much work with the exponential, specifically because there's no way you can make that exponential 0. So I'm going to just go ahead and factor that out. And I'm going to say e to the negative dot, 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 all that stuff I had, times 2v minus mv cubed over kt. All that's equal to 0. And remember, this is specifically the reason why you took in Algebra 1 and Algebra 2 and learned how to do factoring. Because ultimately, I say that's one of the reasons, at least from a utilitarian standpoint, which is what us physicists and chemists and engineers see math as a tool to some extent. I mean, we know it has other things as well, but in that kind of standpoint, you really think of algebra as a tool to a means. And the purpose for us, at least in factoring, is mostly so that you can simplify algebraic expressions, but more importantly, so that you can actually solve algebraic equations. Because it turns out once you express a polynomial, for instance, as a series of factors, a times b times c times d equals 0, then the only way that's true is if a equals 0 or b equals 0 or c equals 0 or d equals 0, so on and so forth. So obviously the e to the negative can't be 0. So that factor that's left, the 2v minus mv cubed over kt, that has to be equal to 0. So now I'm going to take and set that equal to 0. I'm going to say 2v minus mv cubed over kt is equal to 0. I can clearly divide through by a factor of v, and that will leave v squared up here. And now I'm going to get 2 equals mv squared over kt, like that. So ultimately what I get is v is equal to the square root of 2kt over m. Notice all that's under the square root. So that is the actual most probable solution. So I'll write this as equals v sub p, which is the most probable. I'm going to circle it or box it off in a different color. and just say this is the most probable speed. Okay. Now, technically, I have not shown that the second derivative, whatever it is, I haven't shown that. So in principle, I don't necessarily know that I got a maxima or minima or a point of inflection. Of course, if you look at the curve, which is f of v, it has basically one peak like that. There is no sense that it's going to have any kind of minima. So that should in principle be it. But really the other test, like I said, is taking the second derivative, which is really ugly. But I encourage you to do it. That is sort of the holy grail of the test of this part. So by all means do it. I just don't have time. I'm about 99% sure I've done one in the past on my YouTube channel. So you can just do a search for Maxwell on my YouTube channel and you should find it somewhere. But that's the most probable speed. What we find when we actually do the integral process, we find that v bar, which equals the integral of v times f of v. Again, I'm calling it v now instead of nu like your book is, which ultimately equals, of course, the integral from 0 to infinity of, now I'm going to write 4 pi n times m over k, or excuse me, oops, forgot the 2 pi, over 2 pi kt to the 3 halves. Now, it normally had a v squared in there, but since I multiplied by v, it's got a v cubed now. And then that's e to the negative mv squared over 2kt dv. So that's the integral you have to compute for that. And that ultimately turns out to be, if I remember correctly, that one turns out to be 8 over pi. Let me double check on that. Yeah, that's what it is. Turns out to be the square root of 8 kt over pi m, which is about, if you calculate the square root of 8 over pi, you end up getting about 1.60. So that's about 1.60 times the square root of kt over m, whereas vp, oh, by the way, before I write that so close, let me go ahead and write that this is actually equal to v bar, and then vp is approximately equal to, notice it turned out to be the square root of 2 times kt over m. So this is 1.41 times the square root kt over m. So that is, in fact, another expression we can get. And this is another one, which I'm just sort of trying to compare it. So I'll put it in a little box like that. And then finally, there is a root mean square velocity, which we've already calculated. And the VRMS is equal to the square root of 3kt over m, which is about, of course, the square root of 3 is about 1.73. So this is square 1.73 roughly times kt over m square root. I'll circle this off. So those are the three expressions. Now, if you wanted to do this root mean square one, basically I just showed you that you would calculate the integral above, which is v times f of v dv. If you wanted to calculate the VRMS, we just did it using our formula that the average kinetic energy is equal to 1/2 k, or excuse me, which equals 1/2 m VRMS squared, but that's also equal to 3/2 kt. That's one way to solve it, but you can also show that that's exactly the right answer by taking this integral that I did above, but instead of multiplying f of v by v, you're going to multiply f of v by v squared. So you end up having an integral with a v to the 4th power in it. And then when you're done with that, you got to take the square root of that. And that would give you the 3kt as well. So that's really the last type of example that this chapter 18 needs to show. Does anybody have any questions on that? Nothing. Let me put my chat window up too, because I know sometimes people reply in chat and I don't see it. So I want to pay attention as best I can. So no questions on that one. Everybody's cool on that. All right. So as I told you, I'm shooting for September 10th, 11. You guys meet on Tuesdays and Thursdays. So that would probably mean sometime between now and Monday, I will post the tests, or now and maybe even Tuesday, but probably definitely by Monday since we're off on Monday. I will post the tests before then, and then you'll have, since you guys meet on Tuesdays and Thursdays, you'll have until Monday the 11th to complete test one, which is an online test. Remember, my rules are it's open notes, open book, open any book, open Google searches, but you have a very limited amount of time. If you go over the time, you will have huge deductions. Like the normal deduction is 1 second to 60 seconds over is going to be 10 points. 61 seconds to 121 seconds over would be 20 points deducted, so on and so forth. So just don't go over the time. That's the only way I can find that is reasonable and fair to do an online test, because otherwise, if I told people they couldn't do A, B, and C, they would probably do, some of them would do A, B, and C, and other ones would sort of be screwed over for doing the right thing. So I just decided to not stop doing that and then count these tests very little, because I have no idea who's taking them for you. Obviously, I suspect all of you are taking it yourself, but in principle, someone could game the system. So that's the way the practice tests do. Not only that, I give you usually 2 or 3 attempts, and only the highest count. So that should help you as well. The only thing you're really not supposed to do that I consider cheating is, again, if someone has had opportunity to see the very test that I post, whether it be today, tomorrow, Saturday, or Sunday, or Monday, or whatever, if someone's seen that test and then discusses it with you in any way, or creates a website, or creates notes after seeing it, and then you look at that website, or you talk to them about that, or you look in those notes, that's cheating. So that's the only thing you're not supposed to do. Other than that, then you're completely free to use other books, use other notes, do Google searches. The deal is, I put it short enough amount of time and a long enough amount of time where you should be able to do all the problems in the time allotted. And you should probably even have enough time to be a little confused about one particular problem and maybe can't remember some aspect of it. And a quick Google search will probably remedy that. So that's really what I'm shooting for here. So if you're working the practice test repeatedly and you're consistently getting, 80, 90, something like that, then chances are you're in a pretty good spot to take the test. But if you're repeatedly not getting at least an 80, then you probably need to take more practice tests. All right, one more time. Any questions, anyone? Okay, looks like everybody's good. Okay, so what I'm going to do now is I'm going to go into chapter 19. And chapter 19, let's stop sharing the screen for a second. And I'll share the chapter 19 screen. So chapter 19 is called Heat and the First Law of Thermodynamics. And that's really what we're covering. So I will tell you as an introduction, the first law of thermodynamics is essentially a statement about the conservation of energy. The way we do it in physics and chemistry, we're generally talking about sort of chemical energy, which is the energy that are in chemical energy and internal energy, which is the energy of kinetic energy, for instance, that the atoms and molecules have. Not only translational, which is what we were doing in chapter 18, that's translational kinetic energy. The velocity the entire atom or molecule has by going in the left-right direction, the in-out direction, or the up-down direction, for whatever direction you consider to be left, right, up, down, in, out. In other words, if we're at the North Pole, it's like this, but if we're at maybe if we're at North Carolina, it's like this. Maybe if it's at Virginia, it's a little bit like that. If it's down here around Australia, it's like that. So that part doesn't matter. But the main thing is 3 translational modes is what goes into the temperature. But there's also vibrational modes. So you'd have, for instance, 2 atoms doing this. That's another 1/2 kx squared version of the energy. You'd also have rotation about that axis. You'd have rotation about that axis. Those 2 are 1/2 I omega squared and 1/2 I2 omega 2 squared. So those are 2 more what we call degrees of freedom. And that's other types of kinetic energy, are other types of energy that the individual molecules or atoms could have. If it's atoms, then a single atom is sort of like a point-like particle, so it doesn't really have the ability to take a appreciable amount of energy to make it rotate or spin or anything like that. So you don't think about that until you get to molecules. So those are the kinetic energies and the other types of energies you might have to have. But you could also have energies of bonding. So for instance, you a long chain of carbohydrates or carbon-hydrogen chain. If you break those bonds, that's some energy you could get out of it. So there's energy in the system based on bonds. There's energy in the system based on nuclear energy. And that's normally what we think of when we're talking in chemistry about the first law of thermodynamics, is that internal energy. But to be honest with you, the whole thing, if you really wanted to widen the first law of thermodynamics, it's not only those, it also includes mechanical energy. So you could include 1/2 mv squared for the whole. You know, if you're talking about a gas, you could talk about 1/2 mv squared of the entire gas in the container that's holding it. You could talk about how high it is above the ground, so you have an MGH. So all those mechanical energies are part of it as well. So I just want to keep your eye on the ball with respect to that. And your book talks about it for a second. So if you're reading your book, you'll see. And again, as I told you, you do want to try to read this so you can get some of the base knowledge, as opposed to just the ability to solve problems. You learn a lot of stuff just by reading the chapters and paying close attention to see what you get. So let's go on to chapter 19. And the first thing we're going to talk about is heat as an energy transfer, and specifically what it was, what it wasn't. But this little diagram here is very important. And let me use, while looking at that diagram, let me use that as the background for me telling you about what people thought early on, or at least like in the times of before Maxwell and even during Maxwell's time, up to a little later when James Prescott Joule, who died in 1889, he had actually already done this experiment. So this is one of the things that they were thinking. So they had energy that they thought of. I'm not sure exactly what units they used. They could have used the energies of, you know, ergs or something like that, or they obviously, before sometime in the 1800s, they wouldn't have had the Joule to use, because Joule was just a dude who worked in making cannons and brewing beer and stuff of that sort. But the idea was there was these energies associated with mechanical energy that everybody knew about. So we had potential energy and kinetic energy, and that stuff was measured with some specific unit. Ultimately, we decided to use the energy of the Joule. You could have used, for instance, the British thermal unit or something like that. I don't even remember what an erg is, to be honest with you. I know a dyne's another unit of force, but the erg, I think that's energy. Anyways, but the Joule is what we now use. But back then they didn't use necessarily the Joule, because obviously James Prescott Joule, who's it's named after, wasn't around. So they used that unit to talk about energy in mechanical form. And then they had a whole different thing that they thought of as heat. And heat they thought of largely as a fluid. It was a fluid called caloric, and it would flow from one object to another. And ultimately, they were able to decide that it wasn't a fluid, which is good. But what one of the big experiments was this one shown right here by James Prescott Joule. It's more than just a conversion factor, which is sort of the way you treat this when you're in high school, when you come across this for the first time. Maybe it be in our physical science class or in a chemistry class, where it says that 1 calorie is equal to 4.186 joules. So yes, it is a conversion factor, but it's a monumental change of paradigm, specifically because at that point, what they realized, is this thing we call caloric is just another form of this thing we call energy, mechanical energy, but in this case it happens to be a chemical energy or some other kind of energy associated with atoms and molecules. So this was a really big deal. And basically what he did was he attached a weight hanging over a pulley, and of course if you let that weight fall, a certain amount of potential energy decrease occurs. In other words, the initial potential energy would be mg times the height of that weight. But if it falls all the way to the bottom, then all that energy has been transferred into a kinetic energy of those little paddle wheels spinning around in there. Now, those paddle wheels spinning around in there tends to make the molecules and atoms in the liquid, for instance, speed up. But they're not speeding up in a random way. They're actually speeding up in a very uniform way, in a spiral or circle, if you will. So that's not really increasing the temperature. But as those atoms do that, those atoms or molecules, they run into other atoms and molecules. And what ultimately happens is, because of that higher speed of those uniformly moving atoms and molecules, they eventually bump into all the other atoms and molecules until the net kinetic energy on average of all the atoms, and I'm talking the random kinetic energy at this point, all of that random kinetic energy has gone up a little bit. That going up a little bit is the very definition of a change in temperature. So what he was able to show was this mechanical energy, mgh, had an equivalent in the chemical form of, calories or some sense. And that was a monumental discovery. So with that, we were able to figure out, oh, okay, so there's not really like two different types of energy. There's actually just one energy. Sometimes we use the unit of the calorie to calculate it. Other times we use the unit of now the joule to calculate it. So that was a really big deal. And it can be as simple as, for instance, if you, let's say you fire a gun into a tree on purpose to get an estimate of how fast your muzzle velocity is or something like that. If you fire it into a big enough tree, then the bullet's not going to make it through the tree. But you could, in principle, figure out exactly how hot the bullet and the tree got from the bullet impinging upon the tree. And then you could use that energy and say, oh, well, that all came from the kinetic energy of the bullet and the compressing and all that stuff. So you could say 1/2 mv squared for the bullet is equal to mc delta t for all the different parts of the tree and the bullet that got heated from being shot into the tree. That's another example of how mechanical energy can be transferred into this caloric. Okay. Any questions on that? All right, so let's start off with, in fact, I'm going to do a problem just like example 19.1, or actually I'll probably do example 19.1. Let's stop sharing this page. And now I'm going to start sharing my iPad again. So let's just wait like an hour and then it'll come up. Oh, wow, that was the fastest ever. Wait a second. Am I on the right one? Oh, of course not. There it is. Well, if I do the wrong one, it comes up really quick. But when I do the correct one, it takes forever. It's still there. Still trying. There it is. Okay, so the problem was, and I'll read it again. You can see it in your book, but basically it says, suppose you throw caution to the wind and eat 500 calories of ice cream and cake. To compensate, you want to do an equivalent amount of work by climbing stairs or a mountain. How much total height must you climb? So there's a key aspect here, which you might not have saw on the previous page, and especially if you haven't read the chapter already. But there's a couple different units that we're working with here. One of them is 1 calorie. That's lowercase cal. And 1 calorie is equal to 4.186 joules. But there also happens to be 1 calorie, and that's what we call a dietetic calorie or a dietary calorie. That calorie, which is also spelled the same way, it just has a capital, that's actually 1 kilocalorie. And that is actually equal to 4.186 kilojoules. So when this person eats 500 calories of ice cream and cake, they're using a capital CAL. Okay, they're using the capital C before the A and the L. And what they want to know is how high would the person have to climb? So, and that's to burn off those calories. So let's take you can take any mass of a person. I would say a 50 or 60 kilogram person might not have a very good reason to be worried about their weight in a sense. They're probably 50 or 60 kilograms, unless they're, 2 foot tall. Their BMI is probably just fine, and they might be actually causing more harm than good. So I'm going to take a real person. I'm going to take a fat dude like me, and let's say my mass is 100 kilograms. I wish my mass was 100 kilograms. That's like 220 pounds. I am not there. But anyways, so we'll assume the person has a mass equal to 100 kilograms. And what we're going to do is we're going to say work is equal to mgh, and that's equal to 500 calories. Okay. Now, what we're assuming here is sort of, if I just do this calculation, I'm just assuming the body is sort of 100% efficient, meaning if I need to climb up a height such that mgh is 500 calories, then it's going to take exactly that many calories eaten for me to make that. In reality, though, if I really want to expend 500 CALs, capital C, lowercase ALs of energy, my body's only about 20% efficient. So I actually have to spend quite a bit more. So we'll first do that, and then I'll renegotiate with regards to the efficiency of the human body. So what I'm going to do is I'm going to say 500 calories is equal to 500 CAL times 4.186 kilojoules per 1 capital C, lowercase a, lowercase l. Okay. So when I do that, I get 500 times 4.186. That gives me 2,093 kilojoules. Okay. Now I'm going to set 2,093. I should have written this before. Solution. Now I'm going to set 2,093, which is one extra sig fig, by the way. I should put that because I'm going to pretend that 500 calories is a whole 3 sig figs, and the 100 kilograms is a whole 3 sig figs. So that's times 10 to the third joules is equal to 100 kilograms. Notice now I'm using MGH times 9.80 meters per second every second times H. So what I want to solve for is H. So I'm going to take the 2,093, I'm going to multiply that by 1,000 because I need it in joules, not kilojoules. Now I'm going to divide that by 100, and now I am going to, I did that right. Okay, now I'm going to divide by 9.80, and that'll give me H. And in fact, H is equal to 2,136 meters. So 2,136 meters is basically, remember, that's about 39 and a quarter inches or so. Which is 6,985 feet. So that's a good fraction over a mile. So it's like a mile and a quarter high. That's, you've got to, climb to the top of the stadium in Denver, Colorado, to get that height. That's a pretty big climb, but it is doable, at least. So we could, at least if we're willing to climb that much. Now, remember, we also have the efficiency of the human body is only about 20%. So really, we should be able to go only about 20% as far and still burn as many calories. So in fact, taking into account efficiency, H will become 0.20, because I'm saying this is approximately 20%, times 2,136 meters. So 2,136 times 0.2 is 427.2 meters. So that's quite a bit less. To give you an idea, again, in feet, that would give us roughly 1,397 feet. And this one would have been, of course, I did 2,136 and 2,136 times 39.25 and then divided by 12. That was 6,986 feet. So that's how that works. Anybody have any questions on that one?
You get me confused with efficiency. So it's 20% efficient, meaning what?
That means if your body needs to put out, let's say your body needs to put out 1,000 calories. That means your body is going to have to take in enough calories so that only 20% of that is 1,000. So if you divide 1,000 by 0.2, that would be the total number of calories you put in. So divided by 0.2 gives you 5,000. So in other words, if you wanted to expend 1,000 calories doing work, meaning the work itself actually takes 1,000 calories, then your body's going to spend about 5,000 calories doing that.
Okay, thanks.
Does that make sense? Okay. Anybody else have any questions? All right, so the next part is we're going to talk about internal energy, and specifically the internal energy of a collection, say, of gas. So the internal energy in general, in this book, we're going to use the symbol for internal energy. We use EINT. That's the internal energy. And really what it is, as I mentioned before, that's supposed to be the sum of all the energy of all the molecules inside of whatever system you're looking at. So if you want to talk about the internal energy of a gas, then you'd say, okay, see that gas over there? It's 1 cubic meter of gas. It's in a container, but I'm just thinking about the gas itself. Let's look at all the different types of energy that could be in there. And as I told you, obviously all the atoms and molecules are moving around with translational motion. So that gives you 1/2 mvx squared, 1/2 mvy squared, 1/2 mvz squared. And that's just for the translational motion of the atoms or molecules. If some of the molecules are actually spinning as they normally do at least at some critical temperature, then you're going to have a 1/2 I omega squared for each axis about which it rotates or spins. And then, of course, if you have them vibrating along a bond, then that's going to be a 1/2 kx squared for each of those. So those are some of the energies that go into internal energy. But as I told you, you could also have other types of energy associated with, for instance, the bonding of molecules and all sorts of stuff like that. So the big thing is ultimately you should be able to determine or distinguish at least from the difference between temperature, heat, and internal energy. So for instance, if you put an object, let's say I have a solid steel block, and the solid steel block is like 4 tons, okay? And it has a ton of internal energy. And then you put it next to a 1-ton aluminum block, and that has a lot less internal energy. So do we know whether heat's going to flow from the iron 4-ton block into the 1-ton aluminum block, or is it the other way around, or do we just not know? Can anybody answer that?
Well, I know things have a tendency, heat tends to dissipate.
Mm-hmm. That's right. It does in some sense, and we'll make more sense of that as the semester goes on. Would you expect the heat to flow from the big 4-ton block into the 1-ton block, or do we just not know?
I would say yes, from the big steel to the aluminum.
And I baited you into that, just to be clear, because that is what most people think. And in actuality, that doesn't really matter. Let me give you a different version, and it might make a little more sense. We didn't know anything about the temperature of the iron block and the temperature of the aluminum block. We just knew that the iron block, obviously, for starters, just having 4 tons instead of 1 ton means it's probably going to have a lot more internal energy than the 1-ton one. And in fact, I told you explicitly it did have more internal energy. But let's imagine this. You jump into a lake. Now, a lake might be, you know, several hundreds of acres in surface area, and it might be at some points, you know, 20, 30, 50 feet deep, right? I think I just said 50. So that's a ton, or actually that's a lot more than a ton of water. But the temperature might be 68 degrees, and you jump in there and your body temperature is 98.6. Now, it might feel good initially. In fact, especially if you've been working out or running, or maybe just finished climbing a mountain because you ate some cake and ice cream, it might feel pretty good to jump in that water for a second. But does heat flow from the actual river, or from the actual lake, into your body because of that huge internal energy the lake has? Or does it flow out of your body into that lake?
The human body will try to heat up the lake.
Exactly. Your body will try to heat up the lake. And in fact, even if you're somewhere like we learned, well, this isn't a good example because this goes beyond, but we learned the surface temperature of Florida a couple times, and for a good duration of time, the surface temperature of the ocean water in Florida was 101. That's actually higher than human body temperature. But in general, it's almost never as high as human body temperature. So in general, even if the water's 96 degrees Fahrenheit, if you get in there, you can stay long enough where you will ultimately develop hypothermia. So yeah, heat flows from a hot object to a cold object. And what I mean by a hot object is an object that has a high temperature. Okay. So it's not the internal heat or the internal energy that compels heat to flow from the thing with high internal energy to the thing with a low internal energy. In fact, it's the high temperature that compels the thing with a high temperature to give heat to the thing with a low temperature, no matter what the internal energy is. And then by seeing that, you see, oh, heat is just the thing that's being transferred back and forth. And that's the key to understanding the differences between temperature, heat, and internal energy. Does that set it a little better in everybody's brain? Anybody have any questions about that? Okay, so let's think about why that is, and then hopefully this will seal the deal that you completely believe me. And I will tell you that there's just tons and tons of experimental evidence that has been accumulated literally from ancient Greece to now that all points this way. Some of it for a while we were confused about, so we didn't quite get all the details, but now we've sensed it out, and this is the first law of thermodynamics and the second law of thermodynamics are as unshakable as any theory could possibly be in physics. Meaning, yes, it takes exactly one experiment result done well to completely say it was wrong, but we've never found such one. We're not any sense confident that it's ever going to be found wrong, but we always have to keep an eye out for it because there's some new science to be learned when that happens. So let me explain to you from the molecular theory or the atomic theory of matter why that's so. So if you take, for instance, this tape measure and this calculator, and you stick them up against each other. Okay. Now it happens to be both of these have been sitting in my house all day, so they both reached equilibrium with the house and the air temperature and all that good stuff. And in fact, this one, the calculator, is made of plastic, which is a conductor, but not nearly as conductive as this metal Lufkin tape measure. So in fact, when I feel this one feels cold to the touch. This one feels a little cold to the touch, but not nearly as cold as this. That's because your body's not very good at detecting temperature. It's very good at detecting heat flowing in and out of your body. So when I'm doing this and I feel it feeling really cold, what I'm sensing is the fact that this tape measure is a pretty good conductor. So it feels really cold because it's taking my body heat, because specifically my body is at 98.6 and this is probably at 72. This too is probably at 72, but if we imagine them, let's imagine this one being at 72 and this one being at 50. What happens then is all the molecules and atoms of this one at 52 have an average kinetic energy associated with that 3/2 kT. So the kinetic energy of the individual molecules and atoms in the tape measure, if it really is 72, is considerably higher than the kinetic energy of the molecules and atoms in this calculator if it's 60. So its temperature is 60. I'm saying Fahrenheit here, but obviously we can convert it to Celsius and that sort of thing. But the main thing is, because this one's hotter than this one has way more kinetic energy in the individual molecules and atoms than this one does. So every time one of these atoms from the tape measure bumps into one of these atoms or molecules in the calculator, it actually gets a bump. It's like getting hit by a lineman when you're a wide receiver or a safety or maybe even a punter. Okay. So you're getting hit by this beast that's, got a huge amount of kinetic energy. All of a sudden, that particular smaller atom, that punter or whatever, is now moving with a much higher speed. Now, that is not temperature again, but because that one has a higher speed, as does every other one that's been bumped by any of the atoms or molecules in the tape measure, they're going to go off and eventually they're going to bump so much into the other atoms and molecules in the calculator that the net kinetic energy on average will increase for all the atoms and molecules within the calculator, and therefore the temperature of the calculator by definition goes up. So that's what the real heat flow is at the microscopic level. It's literally high kinetic energy atoms and molecules bumping into low kinetic energy atoms and molecules. And it also gives you an idea that when you convert energy into heat like that, it's very unlikely that you're ever going to get any of it back. Because imagine what you've done is you just let some random atoms and molecules bump into some lesser energetic random atoms and molecules, resulting in all the atoms and molecules having slightly more, in some cases, slightly less, or actually it's all of them are going to have more kinetic energy, but some of them will have more to reach that level than other ones will, because some of them had a slightly lower kinetic energy. Now, what's the odds that you can pull exactly the right amount of energy out of all those, 10 to the 22 or maybe even 10 to the 44 atoms and molecules and get it all back? It's nil. That's where the second law of thermodynamics comes in. And a version of the second law of thermodynamics could basically be stated that once you convert energy into heat, that's sort of a bastardized version of heat, and you're never going to get it all back. Okay. So heat is heat's a bastardized form of heat. Heat is a bastardized version of energy. And in that sense, and I don't want to say bastardized in the purely negative sense. I just want to say it's not the kind of energy that you can readily pull right back out. So it's not as valuable in some sense. So that's really where we're going to go with chapter 20, is the second law of thermodynamics. So now that we've got all that in place, we can start thinking about other things. And specifically what I want to think about is I would like you guys to think about what specific heat is and what does it actually take to warm something up. So we'll start by, when I go into this, I'm going to start by taking and considering, for instance, the thermal energy of an ideal gas, basically. So specifically, your book talks about, it says, let us calculate the internal energy of N moles of an ideal monatomic gas. So by restricting ourselves to an ideal gas made of monatomic element, that means an element that has single atoms. So I'm not even talking about H2 or O2 because they're diatomic. That's two atoms together to make one molecule. So we're talking about single point-like atoms. So the reason being is now we can't have energy of rotation, because what kind of energy does it take something whose radius is 10 to the negative 10 or 0.5 times 10 to the negative 10 meters, and whose mass is 10 to the negative 27 kilograms? The kinetic energy associated with a rotating atom is nothing, especially when you compare it to that mass moving at, Mach 2 or Mach 3, in other words, 3 or 4 times the speed of sound. So in dealing with a monatomic gas, we can eliminate those other degrees of freedom that I talked about. So that's what I'm going to do now. So if you take, for instance, N atoms, then the internal energy of an ideal monatomic gas, let me change color here. So ideal monatomic gas. So an ideal monatomic gas has an internal energy E internal, and like I said, our book uses E sub int for internal. Most books use U for this. I'm okay with the internal, doesn't bother me, but I just want to let you know in case you get in your chemistry class and they talk about internal energy and they use U and it looks different. There's going to be a difference in the second our first law of thermodynamics too, and so we'll discuss that when we get there. But what we're saying is, at least if we're talking about a monatomic ideal gas, remember those rules that we use in the kinetic theory suggested that we sort of pretended like the atoms didn't have any affinity for each other or anything like that. And since they're atoms, they don't have any bonding energy, where we don't picture them as something you can break apart at all. So you don't have to think about nuclear energy. So the only internal energy it has is the energy of kinetic energy, which is N times 1/2 m. And now here's where we go V squared bar. In other words, what we're talking about is the root mean square velocity squared. So that's really what the kinetic energy is. Now, we also know that kinetic energy is equal to 1/2 mv squared bar, which is what we just wrote. But we also know that's equal to 3/2 times kT. So we've already used that. So that brings us to E internal is equal to 3/2 N times K times T. And that is a very important expression. And in fact, your book numbers it. So like I've told you before, the rules are in my class, I allow you an equation sheet. You should be making them up yourself in case I don't get one made up for you. You should have one already ready. And right now, the equation sheet would be allowed to include this one, because if you look in the textbook, there's a parenthesis next to it. And actually, let me look at it real quick. There you go. It says 19-1A. So the fact that it has that parenthesis with those numbers and then the closed parenthesis next to it means that's an equation that the author might think is important enough to call back to. And therefore, I think it's important enough for you guys to use as a final result. If there's an equation in a book that doesn't have that, unless I explicitly tell you, you're not allowed to use it. Okay. So that's one version, but we also knew another version of the ideal gas law where PV was not nRT, not NKT. So you could replace this also with E internal is equal to 3/2 lowercase n times the ideal gas constant as we do it in as we do it in physics, not in steam table thermodynamics, where it has a different R value for each individual element or compound. So this too is a labeled equation. And in fact, your book labels it 19-1b. So that's two versions of the internal energy for an ideal monatomic gas. As you can tell, I've been hinting towards this for some time because I keep telling you about these extra degrees of freedom that I sort of count by keeping things that go like the square of something. Those types of energies like 1/2 kx squared or 1/2 I omega squared or 1/2 mv squared. Each of those types of energy is another degree of freedom. And if you're talking about with a specific value like 1/2 I omega squared, there's one I if the atoms in a non-monatomic ideal gas, if they spin this way versus spinning this way, that's two different moments of inertia, and therefore that's two different modes of or what we call degrees of freedom. Same thing with vibrating, 1/2 kx squared. The molecular bond or the atomic bond between two atoms in a molecule, that could have a 1 K value that you use, and then another bond would have a different K. So that's two more degrees of, that's two different degrees of freedom. So we'll talk more about that as time goes on, but I wanted to get you set up on what internal energy is. Now on the next thing that I want to go on to is, again, now that I have that, I'm going to think about specific heat. And specific heat is, in case you are not aware yet, which you probably are, because I think everybody said they've had at least some chemistry before, but specific heat is a body's or an object's or a substance's, and that's probably the best way to say it. It's a substance's reluctance to change temperature, okay? So a substance like water or tin or lead or iron or CO2, each of those substances has a reluctance to change temperature. And the higher the specific heat for that substance, the more reluctant it is to change temperatures. So high specific heat means it takes a buttload of heat to change the temperature by 1 degree Celsius. And in fact, we specifically used water to create our caloric system, our calorie system. So what I'm going to do is tell you, we're going to use the symbol of Q for heat. So Q equals heat added to the system being studied. And the reason I say that is I want you to understand a positive amount of heat means heat is flowing into your system. A negative amount of heat means heat is flowing out of your system, okay? Now, what I'm going to say is that if you add heat, okay, and you're trying to increase the temperature, say, then the amount of heat you have you have to add has to be directly proportional to the change in temperature delta T. What I mean by that is, obviously, if I'm changing from 1 degree Celsius to 2 degrees Celsius, that's going to take a certain amount of heat for a certain substance. But if I'm changing from 1 degree Celsius to 11 degrees Celsius, that's going to take a lot more heat. In fact, that means Q and T are thumbs up, thumbs up. And it just so happens that it works fine with the exponent on delta T being 1. Now, let's think about another scenario. If I go to add heat to a particular substance and I want to change the temperature just 1 Celsius degree, say, would it take more heat to add to be added to 1 gram of water to change it 1 Celsius degree, or would it take more heat to add to 1 kilogram of water to change its temperature 1 degree Celsius? Which one would take more heat, the kilogram or the gram?
Kilogram.
Yes, it's 1,000 times more mass. So yeah, so that means the Q is also proportional to the M. At this point, you know from basic algebra 1 that if you wish to make a direct relationship like this into an equals, you need a constant. But we need one more factor to be taken into account, and that factor is, what is the substance? And I've already told you that specific heat is defined such that a large specific heat means it takes a large amount of heat. So I'm going to say it's also proportional to the specific heat, which is the symbol C. And in principle, there could be another constant there, but we just keep it at that. So ultimately, what we find is that heat added to a system Q is equal to M times C times delta T. And the specific heat of water, CH2O, I'm not trying to write that as a capital, it just looks like a capital. The specific heat of H2O is 1.00 calories per gram Celsius degree. And remember, Celsius followed by a degree means it's expecting to be multiplied by a difference in temperatures. And that difference in temperatures could be, 38 Celsius minus 37 Celsius, or it could be 52 Kelvin minus 51 Kelvin. Both are equally acceptable because the change in a degree for Celsius is the same as 1 unit change in the Kelvin system. Okay. Now, specifically, the original calorie was defined to be the amount of energy it took to raise 1 gram of water 1 Celsius degree. And they set at a very specific temperature. I can't remember the temperature off the top of my head. I want to say it was like from 14.5 to 15.5 degrees Celsius or something like that. That was the original assumption. Okay. So in reality, if you were actually doing a big engineering type product where it's very important to get exactly the right result, then you need to check the specific heat that's closest to the range of temperatures you're dealing with. Even though water's supposed to have 1, well, that's water at 1 for a specific temperature range, which again, I told you I can't remember off the top of my head, but for some reason I was thinking it was like from 13.5 to 14.5 or from 14.5 to 15.5. I might be completely wrong, might remember completely made up that, but that's what I seem to recall. So do always do that when you're doing engineering. You always want to check your constants and make sure you're choosing the appropriate one. Or maybe even breaking it up into several steps so you can have one for this interval and then another one for this and another one for this. That's reasonable too. But that's where the calorie is defined. So 1 calorie is actually 1 calorie per gram Celsius degree is actually a very high specific heat. So as a reminder of that, let me refer you to, there's a table of specific heats. And the word specific, by the way, means per unit mass. It sometimes means per unit mole or something like that. And it's always a lowercase. So if you see a capital C, what they're referring to in that case is the not the specific heat, but the heat or another word for it, basically. But the main thing is they don't use the word specific until you actually divide out the mass, or in some sense, the amount of the substance. So we'll run into that a little later in chapters 19 and 20. So there is a table of specific heats, and that table is 19-1. And I can't really give you what page that's on because we're using an ebook, but the main thing is if you want to look at specific heat in calories per gram degree Celsius, first off, you got to take your pen off of eraser mode. So calories per gram Celsius degree, if you look at, for instance, water, you get 1.00. Again, I'm telling you for a specific value. And in here, let me see. Yeah, they're saying right here that's at liquid at 15 degrees Celsius. So that makes me believe from the table that it is 14.5 to 15.5. So I might be right about that. But that's the specific heat of water, and specifically at 15. Whoa, I can write better than that. At 15 degrees Celsius. Okay. Whereas ice, and in this case, ice at -5 degrees Celsius, that has a specific heat of 0.5. And steam, again, water, and that's at 105, or excuse me, 110 degrees Celsius. In that case, is 0.48. So you see that just changing state does make the specific heat change. But now let's look at things other than water. So let's look, for instance, at aluminum. For aluminum, it's 0.22. For copper, this is really amazing. For copper, it's 0.093. So that's really small. If we want iron, that's 0.11. And if you want, for instance, let's say glass, I think they have something in here with glass. Yeah, they do. For glass, it's 0.20. So the specific heats you can see are quite small for everything, more or less, except water. Once you start to get to water, it's quite a bit higher. In fact, the only thing that's anywhere close to water on the table that they gave us really is ethyl alcohol. That's basically 0.58, ice and steam. The human body on average is 0.83, and a protein is 0.4. So that's kind of what it's about. So let me give you an example of how this is done, because we're starting into calorimetry, and next time we'll do a full calorimetry calculation. But right now I'm going to do two simple calculations. So first off, we'll say example, how much heat is required to raise the temp of 20.0 kilogram, let's say of a 20.0 kilogram aluminum cooler from 10 degrees Celsius to 80 degrees Celsius. Actually, let's go ahead and make that 3 sig figs. I'm going to say from 10.0 degrees Celsius to 80.0 degrees Celsius. And that'll be part A. And part B, what if it is filled with water at 10.0 degrees Celsius? In other words, in the first case, I'm just going to bring an empty cooler up to 80 degrees Celsius from 10 degrees Celsius. In the second case, I'm going to take the cooler and have it filled with 10-degree water. And of course, the aluminum cooler is 10 degrees as well. And I'm going to bring them both up to 80. So how do we do that? Yes. Somebody asked me a question.
Wouldn't we need to know the volume of the cooler for part 2?
You actually know the reason why is because I just left out the mass with 20 kilograms. But yeah, you would normally need to know that. But I was supposed to give you the mass of the water, and I just forgot to write it in.
Got it.
But yeah, but if you had the volume, that would be super helpful, because then you could say, okay, well, it's a certain amount of water. That's 20 kilograms. I know that the density of water is 1 kilogram per cubic meter or per liter. So you could say it's a liter or something like that. Right. But yeah, good question. Thanks for catching me on that. That would have been exactly the kind of mistake I made. So you saved me a little work anyways. So for part A, I'm going to say Q is equal to MC delta T. That, of course, is equal to 20.0 kilograms times the specific heat of aluminum, which we found was 0.22. That should be actually calories per gram Celsius degree. Obviously, I've got some stuff to deal with there. I will. And then it's going to be 80.0 degrees Celsius minus 10.0 degrees Celsius. Now, I also have to convert that kilograms to grams so it works. So I'm going to say times 1,000 grams is equal to 1 kilogram. So I've got to multiply all that times 1,000 to ultimately get my answer. And in this case, it becomes 20 times 0.22 times 70. By the way, that 70 is Celsius degrees, not degrees Celsius, times 1,000. Oh, great. That didn't work. Oh, no wonder. I said 20 times 0.22 times 70 times 1000. And this gives me 3.08 times 10 to the fifth calories. Okay, and that's lowercase calories. I could also convert that to joules if necessary. In fact, times 4.186, that's equal to 1.29 times 10 to the 6. So that's another figure. Now we'll do part B. And we still have to, in part B, we have to apply this much heat just for the cooler anyways, but now we've got to do an additional amount of heat. So Q additional is equal to 20.0 kilograms of water times 1,000 grams per kilogram, like that, times, now water is 1.00 calories per gram Celsius degree, times 70.0 Celsius degrees. So now I'm going to do this, say, I get 1.4 times 10 to the 6 times 10 to the 6 calories, which is equal to 5.86 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the 6 as well, joules. So you can see that is pretty close to 5 times as much heat. It's at least 4 times as much heat added just for the water. So you can basically see that the water is obviously a much better insulator. Any questions on that one? All right. Another thing you can do, for instance, is you can calculate, if I pour a certain amount of hot liquid into a glass container, how is that glass going to change temperature, and what will be the final temperature of the hot liquid and the cold glass afterwards? So that's the example 19.4 that your book does. I will work that next time and then jump into some more calorimetry experiments or calculations, because we're done. We're out of time at this point, but everybody, of course, is free to go. I will wait for the last person to leave in case anybody has any questions. But that's it. And remember, we don't have classes on Monday. Our class doesn't meet on Monday anyway, so I'm just letting you know the school is closed on Monday. So have a good long weekend, and thank you for coming.
You too, Professor.
Thank you, Taylor.
Have a good weekend.
You too. Thank you. Thank you, Haley. Anybody have any questions?
Yeah, hi.
Yeah, go
I
ahead.
just have a question. I did email you the other day. I enrolled late in the course.
Oh, yeah, that's right.
But now I'm back in the US and back to doing normal things.
Yeah, doing your work, right?
Yes, but I was going through chapter 17, the homework questions, and then there was one problem that I ended up just requesting the answer.
Mm-hmm.
It was, I think the reason I was getting confused. So it was the calculate the volume of helium gas under these conditions,
Okay.
and it gave uh it gave the moles, the temperature, and then it gave a gauge pressure. So
Ah.
I was confused what to do with the gauge pressure. I was using it and it was getting an answer when you treat it as just the regular pressure, but I did not know what to do with the
What that
gauge
was.
pressure.
So normally what happens with a gauge, so the best picture for this is just a little tire gauge. Have you ever seen a tire gauge for like a bike or a car? Okay.
Yes.
So that's an open cylinder. It's open at one end. And it's got a little nub that sticks out and pushes that little button in your valve stem. So when you push that, what happens is the gas inside of your tire rushes through that hole and then pushes that plunger, that little white plunger out where it reads degrees or what, or where it reads PSI or whatever.
Yes.
What it's pushing against is atmospheric pressure.
Okay.
So you are literally reading gauge pressure when you read your tire and it says 30 PSI. What that means is it's 30 pounds per square inch higher than atmospheric pressure. So to convert gauge pressure to absolute pressure, you just add atmospheric pressure.
Okay. So in this case, it said 0.36 gauge pressure.
It probably had
It would be
ATMs maybe.
Yes, ATMs. It would just be 1.36.
Yeah, instead of 0.36.
Okay.
Yep. I
That
will tell you atmospheric pressure 1.013 times 10 to the 5th Pascal, which is also 1.013 times 10 to the 5th newtons per square meter. That's also like 760 torr, 760 millimeters of mercury, and I think 14.7 psi. So all those different values can come in handy.
okay. That makes total. I figured it was something to do with the gauge pressure. I just didn't know. Normally, I'm used to like the gauge, the vacuum.
Yeah, they say it's like one little italics sentence in the chapter that says you must use gauge pressure. So,
Okay.
so, I mean, you must use absolute pressure, not gauge pressure.
Yeah. Okay. I understand that. That makes total sense. That answers that question.
No problem. Yeah, try to skim reading the book as best you can, just to look for little keys like that. That'll help you, especially in the catching up period. And ultimately, what I told my students in the first days is students are not reading books, and I get it. You know, I know it's hard to do, but if you can tame that beast and become the student that can read textbooks, you will be a master. So,
Okay.
so keep trying.
Okay.
All right.
I appreciate it. I'll have more time to catch up this weekend and be back on
No
track.
problem.
So
Yeah, have a good one, and
I appreciate it.
and let me know when you get done, and I'll work on it. What was your last name again? Oh, actually, don't say that on. This might be the. I can see it here. I got it. Yeah, I didn't want you
Okay.
necessarily saying that on because this is going up on YouTube in the next couple hours. So
Okay.
all right, well, have a good one.
Yeah. Thank you. Have a great weekend.
Julia, you still there? Okay, I think Julia's gone. All right, have a good one, everybody.